Hi guys, welcome back to my system design series. If you are new to this video or new to this playlist, then let me tell you that we are covering DDIA book of system design. Up till now, we have completed up to chapter number 7, and from this video, we are going to start chapter number 8, that is trouble with distributed system. In this lecture, we are going to cover the trouble with distributed systems, fault tolerance strategies such as HPC versus cloud, unreliable networks and partitions, unreliable clocks and timing, knowledge, consensus and truth, building reliability from unreliable paths, and at the end of this video we will discuss summary of the whole topics which we have covered. Make sure you watch at 1.5x or 2x for better experience. Okay, so let's start. Let's talk about the trouble with distributed systems. A distributed system is made of many computer nodes working together over a network. Unlike a single computer which either works fully or fails completely, distributed system can fail in many unpredictable ways. The failure of a computer you didn't even know existed can render your own computer unusable. In other words, one part of the system might crash or become slow while other parts keep running. So, these partial failures are non-deterministic. An operation involving multiple nodes might succeed or fail at any time, and you may not even know which node. For example, if you make a request across the network, the packet could be lost, or the remote server could crash after receiving that packet, or the response could be dropped on the way back. It is often impossible to tell. As a result, distributed system will require fault tolerance. That means we must assume the things will go wrong. That is network cutouts, machine freeze, etc. And design the software that could handle all such situations. Even simple sounding situation can go wrong. Imagine a web app that calls an order service to submit users purchase. If this service fails or becomes suddenly very slow, any client code waiting for the response will hang unless it has timeouts or retries. In complex system, one service can call another service. It's a kind of a chain. So any partial failure can be amplified by long chains of synchronous calls. For example, 50 dependencies, each 99.99% reliable, still amount to hours of downtime each month. In practice, this means small faults can ripple through a large application, which makes a tiny outage affect many users. Okay. Any partial failure can be amplified by long chain of synchronous calls. Okay. So now let's discuss fault tolerance strategies like HPC versus cloud. Different large systems handles these faults differently. High performing computing clusters, also known as supercomputers, run big scientific jobs. They use specialized hardware and networks and often assume that it is okay to stop and restart on failures. A common approach is checkpoint and restart. The job periodically saves its entire state. If one node is failed, the job is aborted and later restarted from the last checkpoint. This is like pressing save in a game and reloading if the power goes out. HPC system tolerates the faults by essentially crashing and rolling back because uptime is not as critical. In contrast, cloud internet services must run 24/7 for users. They are built on thousands of commodity machines like cheap servers in data centers. Those are connected by IP networks. These machines fail more often and the network can be slow or unreliable. So therefore you cannot simply stop the services for repairs. For example, instead cloud services are fault tolerant by design. That is, they spread data across multiple replicas, route around failures, and do rolling upgrades one node at a time. For example, if one server in a cluster have a hardware fault or is running slow, the system automatically redirects the traffic to the other node and spins up a new instance. Cloud system assumes that always something is broke. After all, at large scale, we can't avoid the component failures. This lets them stay available. Even if one node or whole rack fails, the service can continue. So, HPC, that is supercomputers, are specialized homogeneous hardware. Tasks can be paused or restarted. If a node fails, the whole job is rolled back to the checkpoint. In this, the downtime is acceptable. Cloud services, commodity servers in the data centers, virtualized and elastic, must serve users with low latency. Fault tolerance is built in. Replicas, auto scaling, and redundancy ensures the service stay up even if some machine crash. Cloud environment often uses the technique like chaos engineering, which we have discussed that it is also used by Netflix to deliberately kill machines and test resilience. Okay, so now let's talk about unreliable networks and partitions. The network itself is a major source of trouble. In distributed systems, all communication is over the network, which is inherently unreliable. Packets can be lost, delayed, duplicated, or reordered. For example, a packet might simply never arrive because of cable unplugged or wireless interference. It might arrive later than expected if network is busy. As we are aware that on the routers there is a long queue. A server could crash or pause. For example, garbage collection it just after receiving a request, so it never sends a reply. The response might get lost on the return path. In any such cases, from client's point of view, it just looks like no reply. You cannot immediately tell that why or even if the request succeeded. The only remedy is usually the timeout and retry strategy. But here, the timeouts are tricky. If you wait too long, the user sees a delay. If you time out quickly, you might retry an operation that was actually processed, which causes duplicate actions. So, a particularly severe case is a network partition, where part of the network becomes cut off from another. For example, a data center switch or fiber link might fail, splitting the servers into two disjoint groups that cannot talk to each other. Each group can see the half of the system and can't see the other half. So, during partition, you must choose how to behave. The famous cap theorem says you cannot have perfect consistency and perfect availability at the same time under a partition. In practice, the system may choose to be available but allows stale reads, that is a eventual consistency, or refuses some request until the partition heals. In any such cases, the partition can lead to data inconsistencies, lost updates, and degraded services. Modern systems mitigate the unreliability by redundancy, and smart protocols. They spread the data across multiple machines and data centers. They use consensus or quorum protocols so that majority of the nodes must agree on updates, preventing split brain. They also carefully tune timeouts based on observed latency. Testing under real or stimulated network failures is essential because network faults are inevitable in large scale systems. Okay, now let's talk about unreliable clocks and timing. Here, the time is another hard problem. Each computer has its own clock, and these clocks inevitably drift apart. We try to sync them using the protocols such as NTP, but network delays and clock precision limits means they are never perfectly aligned. A clock might jump forward or backward during the sync if the machine sleeps. For example, a server's clock time is 3 o'clock 14 minutes and 07 seconds could go backwards if NTP makes an adjustment. So there are two types of clocks in computers. First is time of day clocks, which tells us current time and date or can be reset or synced by NTP. Another one is monotonic clocks, which only ever tick forward and is good for measuring durations. Time of day clocks let the machines agree on a global timestamp but are tricky to use while ordering events since they can jump or drift. But monotonic clocks are stable within one machine but not comparable across machines at all. Because of clock issues, using timestamp to order events or resolve conflicts can fail. For example, here two replicas accept writes with nearly the same timestamp. You might lose one update under the last write win rule simply because one clock was slightly fast. Google's Spanner solution is instructive. It provides the time API that returns the interval of possible clock values, that is, earliest or latest transactions, then wait out this uncertainty window to ensure the global ordering. On top of clock skew, machines can pause unpredictably. Garbage collection, VM scheduling, power saving, that is suspending laptop, or admin restarts can freeze the process for milliseconds or seconds. During this pause, the server is not doing any work and advancing its clocks or other nodes may think it is dead. This is why real-time guarantees are practically impossible in commodity server environments. To handle these, systems sometimes uses leader leases with clock checks and fencing tokens. The storage only honors writes that include a monotonically increasing token so that a paused node can't override the newer data. So these are the very easy thing to understand. So we are not going in deeper. Okay, now let's talk about knowledge, consensus and truth. All this uncertainty mean no single node ever has the whole truth about the system state because the network can fail and clocks can differ. Each machine has only a partial view. The system must therefore make collective decisions. A common principle is majority voting, that is a quorums. Rather than trusting only one node to decide the things like who is the leader or order of operations, the system requires the majority of the nodes to agree. In practice, this is what consensus algorithm, that is like Raft or Paxos, do. For example, suppose we need to pick the leader among these three nodes. If node A can't reach node B and also can't reach to node C because of some network issue, A might think that nobody is alive, so I am leader, while B and C still agree that node A is down. If we let A to act alone, it might make bad decisions. Instead, system should make sure that any decision like granting a lock or choosing a leader requires a quorum, that is at least 2 out of 3 in this case. The way the truth is defined by the majority of consensus, not by any single possible misread node. Additional techniques like fencing tokens. These fencing tokens make sure that a node which have lost its leader lease because it is paused for too long cannot accidentally resume and act as a leader. In general, building knowledge in distributed system is hard. We often say that we only know what majority of the people tells us. Systems may be prepared to answer the questions like, did the write to the node X really happen, by contacting enough nodes or waiting for enough time. Some optimize yield, that is uptime, or serving request at all cost, and accept reduced harvest, that is getting all updates, while others do the opposite. Understanding this trade-off and designing protocols are much crucial. So now let's talk about building reliability from unreliable parts. It may seem hopeless that unreliable network, clocks and machines. Yet engineers do build a reliable system by using these parts. The key is layering, and redundancy. Packets can be lost, reordered, or duplicated. But on top of IP, we use TCP, which retransmits the lost packets, drops duplicates, and reorders segments. As a result, most applications see a stream of data that looks reliable. So, here the key strategies for building reliability are replication, failover and redundancy, retry logic, timeouts and circuit breakers, consensus protocols. Okay, so what replication does? It keeps the copies of data or services on multiple nodes. If one node fails, then you can use it from another node. Failover and redundancy. It uses multiple network paths, disk, power supplies, etc. So a single hardware fault can doesn't bring the system down. Another is retry logic. Automatically retry the operations that might have failed due to the transient network glitches or busy servers. Another is timeouts and circuit breakers. This quickly give ups on unreachable nodes to avoid cascading hangs and back off to prevent overload. Another is consensus protocols. This ensures consistency by requiring multiple nodes to agree before committing. So, in summary, a distributed system can be more reliable than its individual parts if designed carefully. By using redundancy, retries, consensus, careful timeout logic, engineers can mask many faults. The goal is to manage the trade-off so that our services meets its guarantees. For example, 5 times uptime or strong consistency, even when things can go wrong. This requires ongoing testing, which includes chaos or fault injection or monitoring. Think of distributed system as organizing a group project. If one student stops responding, that is a partial failure, you ask the another person to fill in. You can't rely on one person's watch, that is unreliable clock. So you set a common deadline. If school network is down, that is a partition is down, that means one part is down of the partition, some teammates might work on another part of the project until it get fixed. And just as a fourth person, if one gets sick, that is called a replication. Distributed servers keep extra servers, so a single failure doesn't break the whole task. So the result is a robust system that delivers the results even if it may have faced many failures. So that's it for this video. If you have understood all the concept, then please make sure you subscribe to my channel, give a thumbs up and comment down if you have any doubts. Thank you so much for watching.